Okay. So now to answer Vishal's question. All right, let's review because those were 5 long minutes. So here are our monsoon regions, and here is the seasonal cycle over West Africa and over India, and we've seen this very different behavior with a smooth transition and staying kind of close to the equator, and this sharp transition and getting all the way to the subtropics. And we've said that it all comes down to where the maximum MSE is, right? We're gonna have rain where we have the MSE maximum, and then we're gonna kick the ball down the road and ask, so where does the MSE maximum show up? Okay. And so we can think of it either in terms of the dynamics and with what sets these to the phi O or in terms of thermodynamics, but at the end of the day, we still want to know where that MSE maximum is. So the role of land. We're going to look at various quantities, the geometry of land, the distribution of land. So how big of a continent, right? Where is that continent? How many you got? We're going to look at orography. Does your continent decide that it's going to go up instead of just staying at the land surface? And then surface type. Albedo, so how much it reflects short wave. Roughness, how does it interact with the wind and transfer momentum. Evapotranspiration, we can think about how much moisture is in the soil. Plants are really powerful beings, and so they control a lot of the evaporation. And so there's a lot that makes land. We're not really gonna cover all of this because I think after 2 hours I'm done, but we could. But so we're gonna start with an idealization. We stopped with the aquaplanet in the first lecture, and now we're gonna start with putting some continent. This is a continent that crosses the equator, and it's kind of like why that one. We'll figure out later that there was no obvious reason, but here we go. So these experiments have been mentioned before. It has a mouthful of a name: the Tropical Rain Belts with an Annual Cycle and Continent Model Intercomparison Project, TRACMIP. And so we ran an aquaplanet, and we ran these idealized equatorial continent. Slab ocean for the aquaplanet. We put an idealized ocean northward heat transport. How did we do land? What did we decide to do? We put the low heat capacity. We made it brighter than water. Okay, so we changed it a little bit. We put some fudge factor in the evaporation so that it would resist evaporation. Whenever the atmosphere asked for X, the land would give it X over 2. And of course, it doesn't move, so it's not going to transport heat. A lot of these things don't really matter. Turns out that if you have 12 modeling center doing an intercomparison and it's not CMIP, some of them will do their own thing. And so you end up with sensitivity experiments that you didn't know you had. And so it turns out that I can tell you that they don't make a big difference. But here we are. Here is what happens when you look at the rainfall evolution in the aquaplanet and the rainfall evolution zonally average over the continent. And so the main thing that happens is that you end up with a peak rainy season closer to the solstice, right? Low heat capacity, you respond faster. What you don't see in this experiment is any jump to the subtropics. The rain band stays pretty much in the same across these things. So what we called, following Gilles et al., an ITCZ regime. What gives? We can look at how the rain band and the MSC change. And here is the ocean, aqua control. So here in blue, various form of the ITCZ, two definitions. I don't even remember what A and V stand for, but two different papers. But basically, the centroid of precipitation, the precipitation maximum in aqua, and then the MSE maximum, the temperature maximum, and the front, the intertropical front. And so there's some separation at the solstice over aqua. There's a stronger separation over land. But we see that even though the MSE goes farther north, the precipitation doesn't really. So that correspondence is there, but it's not one-to-one. Turns out that taking the zonal mean might be a little bit of a stretch, because if you look at the map view of what happens when you impose this continent here, is something that is not zonal at all in precipitation. So here, the color is surface temperature. And then in the gray is the original ITCZ in the aqua control. And we have the rainfall anomalies in the black contour. So you have these negative, big negative anomalies. Why you get a cold tongue in the ocean without any ocean dynamics is an interesting question, but I'm not gonna go into that. What we're gonna focus on is what I have highlighted here in green, which is our monsoon, right? And so we looked at the zonal mean before, but you see that the east and the west, the east, well, do something different, right? This is not a zonal mean. This is not a zonally uniform response. Okay. So to understand what happened there, we're going to introduce this concept of ventilation, which I think was first proposed, at least with this name, Bacho and et al. This is work done by, together with David Nealon. And so they're looking at the moist static energy budget. H here is MSE. And basically, there's a term in here, is the vertical advection that has an omega. And omega means up means moisture, condensing. That's my precip, basically. This F net is the summer heating, or any heating really, it's the source. And then you close the budget in a steady state when there's no tendency with the horizontal advection. And so this term is what we're gonna call the ventilation. And so here is a figure from a book edited by Schneider and Sobel. And this is the chapter that David Nealon wrote. And so what they did for this experiment is they start out an experiment where there was no ventilation. And so at May 30, this is a time where you can look at precipitation in the North American monsoon and ask, but without ventilation, what would it look like? And here's the contour. So it goes all the way into Canada. And then they impose, they start the ventilation, and that brings the contour down. So within just a week, this rain band has gotten not quite reaching Texas, right? So And the idea is that during summertime, the ocean is cooled than the nearby land. And so MSC horizontal gradients are advected inland and limit the monsoon. So we always think of the moisture coming from the ocean into land, and that helps. But in fact, in terms of MSC, you have cold SSD, lower MSC, and you can actually reduce your MSC, and by reducing your MSC, reducing your rainfall. And so the question then becomes, what aspect of the circulation is responsible for the ventilation in some idealized setting? And so here is a figure from those years. And so they put a continent that is 45 degrees wide and extends across the whole domain here. And so this is a simulation done with QTCM. QTCM is the quasi-equilibrium tropical circulation model. Okay, and so it's a simple model. What it does is it thinks of the atmosphere. Again, it's meant to really be representing the tropics. So it represents the atmosphere with one vertical mode, and has the convection in quasi-equilibrium with the environment. And so they, as we did in TrackMe, they put that heat capacity, and they find that the ventilation gives them a response that is not too dissimilar from what we get with the west coast of the continent being drier than the east coast of the continent. And so in that model, the key part of the circulation was the free tropospheric westerlies. So you get westerly advection, and then the circulation changes within the continent itself. But the key, what they claim is that the key part here is the mean westerly flow, the background flow, that does the ventilation. When you do the same thing in TrackMap, where you have a full CMIP class model, and so you have all your vertical levels, you have all your radiation, you have all your bells and whistles, what do you find? We find that, in fact, is the boundary layer anomalous winds that are key to the ventilation. So we get a similar response in terms of east-west contrast, but when you do the decomposition of the MSC budget, we see that between the surface, closer to the surface and high up in the atmosphere, what wins is what's happening at the surface. And when you look at the composition of the various terms, is this meridional advection of the meridional gradient of the background H that matters most. So, so it's a somewhat different mechanism here, but the same concept of it's the horizontal advection that does the trick. But if it's not just the westerlies, right, of the background state, then unfortunately, it becomes more difficult to predict what their answer is, because the westerlies are always going to be there, right? We had that 3-cell model, you get westerlies, all done, right? But if the key circulation is something that depends, that is the anomalous wind, then you're going to end up with something that tells you that the continental geography and the land properties are going to be more important. And so let's look at what geometry and distribution do to figure out why the monsoons look the way they do. And so we weren't the only people to try and put in idealized continents in a model. And so here is a paper by Zhao and Xi in 2018. And their continent started at 15 north, had I think 100 degrees width, and then they had a wider version and a narrow version. And you see again this east-west difference, but you get barely any rainfall in a narrow continent. And then they changed the placement. They went from this to one that, so here the y-axis is different, so we get to 30 north. Well, here this, the 20 north is here and the 20 north is here in this picture. And it's a very different response. And if you get it started at 20, it's a very different response. So oopsies, right? There's no obvious answer to this question of what happens if you put a continent. What continent did you choose? How big? Where? And these responses are not, so now I put them all on the same y-axis, and you get very different things. I don't think that this is easily explained by just the westerlies of the background flow, because otherwise you would get a more similar response here. So each continent has its own monsoon, and the expansion of rainfall to subtropical latitudes is not at all a given. What about orography? So here, the key paper is this by Booth and Kwang 2010. And what they did was to run a GCM sorry, with the real world orography. And what I'm showing here is the low level entropy, but MSE would be the same. And here is precipitation and the circulation. And so this model, it's in the eye of the beholder whether this is a good simulation of the monsoon, but it's not perfect. It definitely doesn't get the whole maximum over the orography of here, but you get this expansion of the monsoon all the way to at least the Bay of Bengal and the Himalayas there. If you take the orography completely out, right, now you see that this maximum in MSE that was hugging the mountains here is gone, okay? And the rain band doesn't make it to the Bay of Bengal, right? It stays farther south, right here. So, so the claim is that the mountains to the north stop ventilation, stop the incursion by the westerlies, so that when those are gone, right, you can erode your MSE, you can have tropical air, mid-latitude air mixed together, and end up with less strong and less northward of a maximum. They did one more simulation because they wanted to show that the elevated heating of the plateau was not really the thing that would give you these changes, that it was really the fact that the Himalayas constituted a barrier to the ventilation. And so they just put this narrow mountain without having the plateau to the back of it. And their result is very similar to the whole full mountain experiment, right? So you get back your MSE max and you get back your expansion to the north of the rainfall. Okay. So if I had time to go through a full review of all of the monsoons, Now, orography would play a large role in two more circulation. One is the North American monsoon, and the other one is the East Asian monsoon. And there, the interaction with the jets is more dynamical, or where is the jet going to go with respect to the orography. And the papers to go to are here. Booth and Pascale in Nature, and this, and among others, Chang et al. But there's more, but these are the ones I like, and I remembered. But yeah, so orography is important. We're not here when we have to deal too much with the mid-latitudes is really outside the scope of this talk, so we're not gonna go there. Instead, we're gonna move on to the surface type. And in particular, we're finally gonna get to the African monsoon, because we have this big desert to the north. So what does that do, right? So we started out with a continent that was roughly as wide as Africa, placed in the same position as Africa, and we got one solution. That solution did not look at all like the Sahel, right? It was very different from the east to the west. While Africa in the African monsoon, rainfall in the African monsoon is quite zonally uniform. So it makes sense to think about the desert as something that does interfere with the advancement of rainfall in Africa. So to orient everybody, here is our ITCZ/monsoon. Here is the desert. This is labeled as Sahara air layer, and the rest we'll encounter later. All right, so how to think about a desert? So Charnin 67 had this view of the desert as, well, they're bright, they're dry, and they're subsiding, and those things go together. And so here is a picture of that F net that we saw in the equation at the beginning, how much energy gets into the atmospheric column. And so the Sahara stands out among the Northern Hemisphere land masses because you don't, instead of being red, is bluish. How come? Well, we have high albedo, so less short wave. We have a very drought column, so we export more long wave. And so the whole combination gives you this negative F net. And so if you have that, you're going to have adiabatic warming to balance the diabatic warming. What am I saying? The diabatic cooling is balanced by subsidence, right? So, and adiabatic warming, and so that reinforces the aridity. And so the interaction between this and the rainfall to the south was part of Charney's idea of what would create the how do you get a drought in the Sahel by forcing it from the surface with changes in albedo. Now it's contractually obligated to say that Charney was wrong on the Sahel drought of the 70s and 80s because overgrazing was not a thing. I mean, not at the level that you need for something like changing the monsoon. But if you get a good kick from insulation and you can get the Sahara to be green, that is a big feedback. And so that idea works, but not, with some caveats. So let's look at the relationship between the desert and the monsoon. So here, instead of having MSE, now I have temperature. And so we see this hot temperature, and the surface wind confluence line is in blue. So we see that here evolving and coming north and then going back south. And the rainfall in these color lines stays to the south of the confluence line. Again, this is the MSE, and so that stays where the rain band is. We see dry, less MSE to the north where the desert is. That tracks. Okay, so the picture now is something a little bit more complex. We have the inflow that goes into, quite farther north into the desert, but rainfall stays well to the south of where you would have the confluence line. But this is a shallow circulation, and so we should really be careful about distinguishing whether all of this is a monsoon layer or it's a combination of the deep monsoon circulation and the shallow desert, circulation into the desert low. And so another way of putting it is here in this schematic that really highlights the fact that if you have this return flow at mid-level here, 600 millibars, so subsidence over the desert in the free troposphere, but turbulence and upper motion here over the hot desert and return flow of the shallow circulation here, you end up with this Saharan dry layer coming into the monsoon flow and producing dry entrainment and interacting with rainfall that way. And so what that also does for us is explain something important, which is that enhanced rainfall in the monsoon is associated with a northward shift of the Sahara low, not an intensification. So we tend to think of, well, if you, again, because of this land sea breeze that get kind of stuck in our head, right? It's that if you intensify the Sahara heat low, you get more flow, right? And if you get more monsoon flow, you should get a stronger monsoon. Well, no, because it's not a land sea breeze. And so if you are enhancing this flow because it's part of this shallow dry circulation, you're not gonna get an enhanced monsoon, okay? So the updated picture for the African monsoon from that Ni et al. Paper that I keep showing is this, right? So we have the big monsoon cell and we have a shallow cell, and those two do different things. So the shallow has an ascent where theta, the dry energy is maximum, and the monsoon has ascent where the moist variable is maximum. Okay, so then there's something else that happens if you have a strong thermal gradient, and that's by thermal wind balance, you get an African easterly jet. Okay, and so here is the map view, hot, hot, hot Sahara, and here in gray is the African easterly jet at 600 millibars. And what does that do for us? Somebody was asking about synoptic disturbances. This is a beautiful picture of what happens. You get this wave running along the jet, and in these waves you get these systems that develop. And so if you look at how if you look at this in a little bit more detail, you see that in the Sahel, you have a strong amount of variability in rainfall that is associated with this quite fast waves. So here we have all the various convectively coupled equatorial waves, and we've split the Kelvin wave between the high frequency and low frequency, so that blues are the fast guys and reds are the slow guys. And so in this area, in the area of the Sahel, the African easterly waves are really the most important to them. And if you look at the fraction, of how much of the variance is in the high frequencies versus the low frequency, Africa shows up as a bullseye. The other thing is, how much of the, within these waves, but also outside of the waves, just straight from the shear that of the African easterly jet, we also get the development of the mesoscale convective systems. And so in this region, we get about 70–80% of the precipitation coming from these mesoscale storms coming through. And so we are kind of at the end of our survey. And so if we look at what is this diversity of monsoon regime, we really focused on these two. One, where we've explained the circulation with this deep Hadley solstitial cell and a peak in MSE that is makes it all the way up here because it's sheltered by the Himalayas. We looked at the Sahel and we've updated this picture with a shallow circulation that also explains why a hotter desert doesn't give you a stronger monsoon. And then I also wanted to show the whole tropics in terms of the synoptic and interseasonal variability, because Africa is really a weird place, right? It's just everything else has a variability that is quite slow, but here it's all at the synoptic and fast scales. Okay. And so I wanted to conclude this with a couple of discussion items. And the first one is, can we build a model hierarchy that includes land, and how? We could have spent a whole day here showing you papers that have, now we put the soil moisture interactive, non-interactive. We're putting 2 continents instead of 1. And so there's this, if we want to make progress, can we figure out different ways of going about it that thinks of land as something else that we can simplify? And I don't have an answer to this, but it's a very good question. And then the other thing that I've been ruminating about is, we have this dynamical view of the diversity of monsoon, eddy-dominated or AMC-dominated circulations. And we have this thermodynamic point of view with the ventilation. Is there a way to put these two together in a way that is a little bit more satisfying than what I've tried to do for you today? And so this is my summary slide with a schematic of the monsoon that maybe or maybe not touches on all that we've discussed. We have, it's connected to the ITCZ. It's the YZ circulation, Hadley-like circulation is definitely important, but you might get another one. The mid-level and the ventilation by the boundary layer are very important, right? And you get lightning, which you don't get over the ocean, so it's cooler. Not cooler in the sense that colder, cooler in the sense that it's neat. And so here we are. How do I think about monsoons? They are integral component of the Hadley circulation, but they are localized by continents. And so this low heat capacity is important. When you think about how far they go over land, it turns out that they do depend on the rotational flow and the ventilation that it provides. And they're not at all the same across the continent, as I mentioned before, across the many epochs of Earth. That's it.
Yeah, hi. So I have a doubt in a slide where you show about during the active phase of African monsoon, the heat low is sort of displaced to the north, is what you said, I guess.
Say it again.
In one of the slides where you show the dry entrainment is limited in the active period, and during that time, the heat low is displaced to the north rather than not a stronger one, a shallow circulation. Yeah, here. So, if my memory serves right, people say that the African easterly jet is quite strong when the heat low is strong, and that leads to barotropic instability and the generation of African easterly waves. So, how can I understand that, like whether the northward shift of the heat low is the time when the monsoon is active, or it's much closer and we have more barotropic instability and MCSs that's more related with the active monsoon?
Um, so the rainfall is still south of the African easterly jet. Do I have it properly? Well, not so much in this diagram. Is maybe better in here, but you know, most of the rain is still on this side because you do need this deep ascent, right? And so what the jet does is, yes, it does organize these systems, but and so some of that dryness that comes with the return flow sometimes makes those systems more intense, like you get you get more thin and they have time to become even more explosive. But the fact that you get a storm doesn't mean that you get rainfall at the surface. It's actually not infrequent for storms to develop and all of that rain to evaporate before it touches the ground because it has to go through that Saharan air layer. And so we don't care about those.
Thank you.
You're welcome.
Hello. So my question was that, I mean, you showed that in the boost paper that the topographic barrier kind of stops the ventilation. That's why you get a more northward extent of the Indian summer monsoon. But for Africa, that's not true. And you also showed that the African easterly jet kind of looks like a northern limit of the convection that goes, right? But what I want to ask is that if you look into the variability of precipitation, the African monsoon has a really low variability, but the Indian summer monsoon has a higher variability. But even though the mid latitude dry intrusion from desert doesn't come towards India the way it does for Africa, but you still do get some intrusion. Let's say if you look into some of Douglas Parker's work, that they showed that during break phase of Indian summer monsoon, you get some mid tropospheric drying. So do you think even though the orographic barrier is stopping the ventilation, but does that mean you get more variability? Because even though you are not getting a prominent shallow circulation, but let's say from 700 to 500 hectopascal, you get some kind of mid-tropospheric drying, which comes during break phase, and which maybe can uh, like increase the variability a bit much. So maybe do you think that even though the orographic barrier is letting the monsoon go a bit more north, a bit, can that be a possible mechanism to increase the more variability or not?
That's a very good question. Why the Indian monsoon is more variable than the African monsoon? I guess it depends a little bit on the time scale, right? Because the the African monsoon has very strong decadal variability because it's strongly linked to what happens to the sea surface temperature changes. Um, I'm not, besides, yeah, and the Indian monsoon, I guess, variability at the interannual time scale, I think of it as determined by the tropical oceans. And so in that respect, it just, the barrier does that. It keeps, keeps the connection to this tropical ocean maybe more prominent than it is for Africa, where you have more of a connection to this, northern interhemispheric gradient of SST, and the amount of variability that you get out of these two different, sources of SST variability depends on what the SST is doing, and those are completely different processes. Now, at the top of my mind, but probably you guys do know, how much of the variability in the monsoon is can be explained by sea surface temperature, and how much of it is internally generated. What is that number? And if you throw everything at it, like if you have an AMIP simulation, how much of the variability you can get?
The number top of my mind, but I think you still have significant amount of variability
that is unexplained.
Yes, that's unexplained, and we
Yeah.
don't know if AMIP kind of overplays some of the internal variability that would otherwise have been damped by inclusion of ocean. We don't know, I think, but
True.
maybe others know in this crowd.
Yeah. So I don't know, but I think aren't you going to be talking about interseasonal variability? So maybe, so if the rest of the variability, right, is just this atmospheric variability with the interseasonal oscillation, that might explain it. The Sahel doesn't have any of that. As I said, it's all synoptic. It's all this. And so, yeah, but then you still have a big chunk that is, yeah, connected to the just atmospheric internal variability, including interseasonal, right? Yeah, so I don't know that I've answered your question. I think I forgot your question by this, but at the end of my rambling, but.
With the topographic variable,
Yeah.
Creates a drier mid-trop, and which kind of kills the convection. So, I mean, my question was, do you think that even though the orographic barrier doesn't lets the monsoon go way north, but does that mean this mechanism can introduce more variability on the context, which we don't get in the Sahel, because we have a steady dry intrusion goes on all over the season. So,
Yeah, that's a good way of thinking about it.
Can I make a quick comment?
Comment, maybe if it's a comment, maybe he can.
I think there was a paper by Bora et al., I guess, which explained the unexplained variance of deficits that were not associated with ENSO. So that was shown to be associated with the mid-latitude wave train and some dry air intrusion over Northwest India. So I don't remember the exact variance that mode explains. That was probably associated with the Atlantic zonal mode or something. So that can also bring in drought by the mechanism, like bringing in cold, dry air,
Dry intrusion.
dry intrusion at the northwest corner of India.
That's a interesting thing as well. I've seen those. Yes. Your mic is not on, I don't think. Your mic is not on.
this maybe I think this question is more apt for your previous lecture. Maybe the global monsoon you started with the rainfall amount. It's the global monsoons are delineated based on the rainfall amounts. But the regional monsoon is a part of this circulation, the global monsoon. So what I want to view in a way that are we going to a unified monsoon theory that can explain any continental ISOs like North American oscillations or Asian South Asian oscillations, even though they are different as far as the polar propagation is concerned. Can we are going to a unified monsoon theory saying that both can explain the breaks or the active conditions irrespective of the continents?
I cannot. I've given up. So TrackMe was done with on an NSF project that I very boldly called, the essential dynamics of the essential monsoon or something like that. And by the end of the 3 years, like, yeah, there's no such thing. So, but we have a lot of bright young people. I would love to be proven wrong.
Hello, ma'am. In case of India, monsoon onset first happens in Kerala. After that, it gradually progresses throughout the India. So we does not have monsoon simultaneously everywhere in India. Is it the same case for Africa also?
So the African onset, some people think there's a jump between the coastal phase and then the north. I look at that same plot and I don't see a jump. But yes, I mean there's a progression. It's just that it doesn't buy you much because it's not. Maybe Indian is you have a more place to propagate to, and Africa is such a narrow band, and so that the evolution is not as it doesn't give you much predictability. There's plenty of false onsets though there too, where you get the pre-monsoon couple of MCSs, and then you're done for a while. And I don't, the good thing is that there seemed to be some predictability from SST. At least that's the last time I checked, but yeah, I don't know how much you can extrapolate from the first location to the others. Does that answer your question? Thank you.
Further question?
I have one question. So John China, I remember, was trying to contrast African, Indian, and Asian monsoon, the gradual versus abrupt. But I suppose if we what's the update on that? Would like your comment.
So, I mean, I was citing John's work in terms of the interaction of the East Asian and monsoon and the jet, but I don't know of a unifying theory that he's come up with. I might just not be up to date with that, but I'll look it up because, yeah.
Thanks.
Let's thank Michela again for amazing lectures.